Hi everyone. So welcome to the tutorial number 11 or tutorial for week 11. So let us start discussing the problems and these are the practice set of problems as I already always do that these problems will mostly be common with the problems that is all given to you in your current week's assignment. So you can cross check your answers and your method of doing the solving the problem from here for some of the problems, and others will be of the same type, so you can follow that from there. So let us begin. So the first question is, calculate the change of melting point. I hope you can see the question properly. Yeah, calculate the change of melting point naphthalene per atmosphere change of pressure given the melting point is 80 degrees centigrade and the latent heat is mentioned like that in calorie per gram units, and density of the solid is in gram per cc and density of the liquid is also given in gram per cc. So basically you have been given that there is a change in pressure which is 1 atmosphere here because per atmospheric change of pressure, and you have to know what is the change in the melting point temperature, that means what is dt, and you have the melting point temperature actual value, not the change you have to calculate, but the original value is 80 degrees and the latent heat for that melting is also given, and density for both the states is given. So the straightforward equation solution that this problem has is to you have to use the Clapeyron's equation, right? So let me write that down. The first thing is going to be solved by Clapeyron's equation. And Clapeyron's equation has such a form that you say that your dp by dt is equal to L by T V2 minus V1. Okay. Yeah. So dp by dt is L by T V2 minus V1, where dp is the change in pressure and dt is the resulting change in temperature. In this case, the change in temperature of the melting point. L is the latent heat for the melting, which is also given. T is the actual temperature for melting, that is given, and V is volume. So volume is basically mass by density, right? But in this case, because there is no information as such about mass, so the only information you have is the density from solid to liquid. So we can take, and because density is in per mass units, right? Basically because it is gram per cc, so it is 1 gram per cc. Means you can by default consider that your m is 1 gram, and in that case your v will simply be just 1 by rho, right? So in that case you can just use your, instead of v you can just use 1 by rho, taking your mass to be 1. And this is a melting thing, so you are changing your state from solid to liquid and the process is melting, right? And normally the melting point temperature is 80 degrees centigrade, which is like 80 plus 273 Kelvin. Okay. Yeah. So 80 plus 273 Kelvin becomes 353 Kelvin. So I am defining all of the terms that is given to you in the question, and then we'll put the terms and substitute in the equation and we'll get the unknown value from there. Now your change in pressure is dp, which is like 1 atmosphere. Okay. And if you convert this into CGS units, so this is 1.013 into 10 to the power of 6 dyne per centimeter square. This is in CGS unit, and your change in melting point temperature because of this change in pressure equal to dt due to change in pressure is equal to dp. So you have to calculate what is this dt, right? So then and L is given in the question. L is given as I think 35.5 calorie per gram. Let us take 1 second. Okay, So just see that latent heat is also given per gram unit, so you can easily take your total mass unit for the quantity is 1 gram, because nothing is otherwise mentioned about the mass in the question. So just take it simply as 1 gram. Now be very sure that you have to take all the units in the same manner, right? So if you are using CGS units, so you have to use CGS units for all. Like say Kelvin is already, then be it CGS or SI, you have to do it in Kelvin, so that is fine. Then volume is given in gram per, density is given in gram per cc units, which is again a CGS unit. Cc is centimeter cube, you know. And dp was given in 1 atmosphere, which I have converted into dyne per centimeter square, because that is a CGS one. Now this latent heat is given in calorie, right? But remember that this energy, because latent heat is basically energy per mass. Okay, so how much heat energy is needed to convert per unit mass of some substance into the other phase? So that is the latent heat. So but here this is given in calorie units, and you know that normally in SI energy is given in joule units, right? And the CGS unit of the energy is arc, not calorie. Calorie, so you have to convert this calorie into joule and as well as arc unit, so that that becomes in CGS. So there is a relation that 1 kilocalorie is generally 4.2 into 10 to the power 10 arc. So then 1 calorie becomes 4.2 into 10 to the power 7 arc. Or the easiest way is that 1 calorie is, I think, 4.2 joule. So you know that 1 joule is equal to 10 to the power 7 arc. So then it makes it 1 calorie is equal to 4.2 into 10 to the power 7 arc, right? Right, fine. So then you know that your L becomes 35.5 into 4.2 into 10 to the power 7 arc per gram. Okay. So after doing all this, sorry, now we substitute the things that are known in the equation of Clapeyron's equation. So basically then dp by dt is equal to L by t v2 minus v1 was the equation. So from here you have to calculate dt, so take dt to one side. So dt is equal to t p2 minus v1 into dp by L, right? Okay, this is dt. Then this is equal to, so this is like 80 plus 273 was 353 Kelvin. So the T will be melting point temperature, which is 353 Kelvin, into V2 minus V1 is just 1 by rho 2 minus 1 by rho 1, into dP is the change in pressure, which is in this case 1 atmosphere, means 1.013 into 10 to the power of 6 dyne per centimeter squared, and divided by L is 35.5 to 4.2 into 10 to the power 7. So from here you are left with only putting or substituting the density in this case. So this is this was given wholly in what, gram per cc unit, right? So what were the values? So values were 1.145 for the solid initial stage, that is rho 1, and rho 2 is the final stage, which is the liquid state density, which is 0.981. So 0.981 and 1.145, right? So the final stage is 0.981 minus 1.145, right, into 1.013 to 10 to the power 6 divided by 35.5 into 4.2 to 10 to the power 7, right? So here you get that your change in temperature, you will get that calculating this 0.035 Kelvin. because otherwise it is a change in temperature, so it does not matter whether this is in degree centigrade unit or Kelvin unit, because whatever the unit is, the change in temperature value remains the same. But because we have been using Kelvin units everywhere, so we say that this is given in Kelvin units, and basically 0.05 degree Kelvin or degree centigrade will be the change in temperature in this case. So this is the answer. Let us choose the correct option for that. Yeah, so they have also given in Kelvin unit. So this is the third C number option. So you can see that some of the units are in degree centigrade, some are in Kelvin, because I said that the change in temperature value is the same whatever unit you use, because be it you are changing from, let's say you are changing 20 degree, so you are going from 80 degree centigrade to 100 degree centigrade. But if you are changing 20 degree, then also in Kelvin units you can add 80 plus 273 and you can add 100 plus 273, and still the difference remains 20, right? So that the unit does not matter in this case if you are talking about the change in temperature. So even if they would have used that 0.05035 degree centigrade, then also number C, this will be the correct answer for our case, because here unit is irrelevant because we are talking about the change in temperature. So I hope this is clear now. So let us move on to now question number 2. Just 1 second. Question number 2. Yeah. So the sublimation curve of solid NH3 is given by ln P is equal to some equation in relating P and T, and the vaporization curve at liquid NH3 is given by some other equation in P and T terms, where P is in millimeter Hg and T is in Kelvin. The temperature of the triple point of NH3 is what? Okay, so yeah, so NH3 is given in solid state, and sublimation curve, you know that sublimation is changing the phase from directly from solid to vapor. Okay, and the vaporization curve means here the phase change occurs from solid to, sorry, not solid, from liquid to vapor. So in both the cases the equation for the curves is given. So sublimation curve is the curve along which the solid and vapor phase remains or coexists in equilibrium, and as well as vaporization curve is the curve along which the liquid and the vapor phase they coexist in equilibrium, right? And they are both of their equations in P versus T graph if you plot. So they would have a relation or a equation which will have two things, P and T, and that equation is already given in the question for separately for sublimation and vaporization curve. So instantly what comes to your mind is that you have to think about a P versus T diagram, because that's where these kind of processes are basically characterized explained in a P versus T diagram, and how the most important three phases of matter they can coexist or remain in equilibrium or change from one phase to other. In P versus T diagram we can see it all, so I'll be drawing that later while solving this. Now the rest of the question is that the temperature of the triple point of NH3 you have to know, right? So first of all, because this is that type of a question, so we'll be first drawing the P versus T diagram to make it clear where the sublimation curve is and where the vaporization curve is, and where even is the critical point and how is that defined. Okay, so this is, let's say, your one axis and this is the other one. This is your pressure axis and this is your temperature axis along the x. So now there are three main phases, right? Solid, liquid and vapor. Now so first let me draw the sublimation curve one. So this will be going from origin like this up to here. Okay, now it will branch out. You can also find this from any textbook or any lecture material. This is very common and very standard. Okay, so now the fusion curve I will be drawing in blue. That will be having a negative slope like this. So that is a bit I think maybe a bit carved, but it is actually a straight line with a negative slope. Here there is a point that both of the curves meet, and the vaporization curve I'll be drawing in red. This will be a curve, okay, So here there is a point. Yeah, it has become a lot bigger than I expected. So yeah, this is a point, and here also there will be a point. Okay, now let me define what are the different things. First of all, this is your solid phase. Okay, and this is your liquid phase, and this is your vapor phase. Okay, so this curve here that I have drawn in blue is your sublimation curve. Sorry, not sublimation, this is your fusion curve. And here in white is the sublimation. And the red one is the vaporization curve, right? So this point sitting over here is your triple point. So this is your T, let's say TT, and this is your T subscript T. So this is your triple point basically that they are asking in the question, and other two information in the question is this curve, sublimation curve over here, and the other one is the fusion curve over here. So you can see, and this is this one just because I have drawn for the sake of the completeness of the diagram. This is your critical point, or above this is your critical region. Okay. Now, so you can see that this fusion curve is basically a line between the two phases, solid and liquid. Basically, because when solid fuses into changes its phase into liquid, or vice versa, fusion curve is in between that. So this is the curve along which both the phases can coexist in equilibrium. And similarly, sublimation curve is going, let's see that it is between solid and the vapor phase. So this is the curve along which the solid and vapor phase can coexist in equilibrium. Okay, and the process of sublimation happens, key solid changing into vapor. And vaporization curve is similarly between liquid and vapor. So it is a curve along which these two phases can coexist in equilibrium. Okay, so because all of them are drawn in a P versus T plot, so obviously they will have a equation defined to them which will have the two terms P and T. The triple point is the most important one. That this is the point which is at the intersection of all three curves. So basically this is the point where the substance can actually coexist in all three phases. Okay, solid, liquid and vapor. So that is the idea of triple point. That the substance can coexist in equilibrium as an equilibrium mixture of all the three phases, solid, liquid and vapor. Now, so let me write down up to this part. So triple point is where the substance coexists as an equilibrium mixture of its solid, liquid and vapor state. This is the triple point, and it is defined like that it has a particular pressure Pt and a particular temperature T suffix T. So these are the triple point definition parameters mainly. Okay, and sublimation curve is basically sublimation curve will have some PT equation, which is the curve along which solid vapor coexists in equilibrium, and similarly vaporization curve this is liquid vapor equilibrium coexistence curve, right? So after this, once we have defined the main things about this question, now let us move on to solve this. That you have to calculate what is your triple point value when you are given the sublimation and the vaporization curve equations. So you can directly see that both of them has a common meeting point, and that is a triple point. So obviously at the triple point both of the curves will be having the same value. That is the main idea, right? So at triple point, in short TP, both curves, by both curves I mean the two curves given in the question, these two, both curves intersect. Okay, so their equations has to be equated on left hand side and right hand side. Okay, so basically your equations were that first one is ln p is equal to 23 minus 3750. This is the I think, yeah, sublimation curve one, and so let me write that down. That so sublimation curve value at triple point is equal to vaporization curve value at triple point. So your sublimation is basically ln p is equal to 23 minus 3750 by t, right? But if you are talking about triple point, then you have to replace p by pt and t by tt, because those are the values specifically for triple point. And for vaporization, you know that the equation is 19.5 minus 3050 by tt is equal to ln of pt. Okay, so then you equate both of them. 23 minus 3750 by pt is equal to 19.5 minus 3050 by pt. So it becomes, now let us solve 3750 minus 3050 by dt is equal to 23 minus 19.5. So from solving this you get that your tt will be like 200 Kelvin. So this is your triple point temperature, you can easily see. And if they are only asking for triple point temperature in the question, but if they also ask you in the question about the triple point pressure pt, then you can easily solve that out by, because you know now that what is tt, so you can basically solve that from any of the equations. Let's say you can use this equation and you can substitute tt here, and then in turn you can get the pt from here. Similarly, you can also use this equation, you can use the tt here and then get the pt. So both will have the same pt value, so that will define your triple point. So let us now check the option that 200 Kelvin is the answer we obtained. So 200 Kelvin is also the correct answer, right? So it is solved. Now question number 3. So melting point of ice changes by 0.0072 degrees centigrade for a change in pressure by 1 atmosphere. In the saturated vapor pressure of water at 0 degree and 1 degree centigrade at 4.6 mm Hg and 4.94 mm Hg respectively, then find the temperature of the triple point. So you are asked that the melting point of ice changes by some amount. So dt, let's say dt is the amount, so dt is given as 0.0072 degree centigrade for a change in pressure which is dp, which is given here as 1 atmosphere. Now the saturated vapor pressure of water, okay, saturated vapor pressure let's say P for water at 0 degree centigrade is given and 1 degree centigrade is also given. So then you have to know that find the temperature of triple point, right? Okay, so we have to figure out how to um, solve this and get the triple point temperature value. Just 1 second. Okay, so let us solve question number 3, that we have to calculate the triple point temperature value, right? So and the option is let me just check. Yeah, question number 3. So this is question number 3, where it is said that your saturated vapor pressure of water at 0 degree centigrade is equal to 4.6 mmHg. Okay, and saturated vapor pressure of water at 1 degree centigrade is equal to 4.94 mmHg, and your change in pressure is 1 atmosphere for change in temperature of 0.0072 degree centigrade. Now, so for 1 degree temperature change, if you see the saturated vapor pressure values, then for 1 degree temperature change, the pressure change is how much? So this delta P is 4.94 minus 4.6, which is like point 0.34 mmHg is the change in pressure for the saturated vapor pressure for 1 degree temperature change. Okay, now so this you can think of that there is a coefficient of how much the pressure changes with temperature. That coefficient you can name as alpha, and alpha can be here as 3.34 mmHg per degree centigrade. So this is the coefficient we have defined for how much pressure change by unit temperature change, right? So now let's say that, let's assume triple point temperature is T degree centigrade. So pressure at T degree centigrade will be pressure at 0 degree centigrade plus the coefficient of how much the pressure change with temperature into the change in temperature, right? So you know that the pressure at 0 degree centigrade is 4.6 mmHg plus this coefficient is alpha into delta T. Now 4.6 plus alpha is here 0.34 in mmHg, and temperature change from 0 to T degree centigrade is simply T minus 0 or T. So because it is a change in temperature, so it does not matter what unit we define it at, but this is just T minus 0, and the whole thing will be in mmHg unit because that is the pressure unit we are using here. So this is becoming 4.6 plus 0.34 times T mmHg. This is the pressure at triple point, which is T degree centigrade, right? Now, how much is the decrease in pressure then at T degree centigrade due to the temperature change from 0 to T? If you have to calculate how much is the decrease in temperature, decrease in pressure, then you have to take the difference. So, how much does pressure decrease when temperature changes from 0 degree centigrade to triple point T degree centigrade. So that is simple, because you have to take the pressure which is at 0 degree centigrade, pressure at 0 degree centigrade minus pressure at T degree centigrade, right? So in normal case, you know that at 0 degree centigrade, so the pressure value is 760 mmHg minus the pressure at T degree centigrade is 4.6 plus 0.34 T. This is in mmHg units, right? So this is the change in pressure. Now you know that your how much is the rate of change in pressure versus temperature is delta T is equal to 0.0072 degree centigrade for delta P is equal to 1 atmosphere, okay, which is like 760 mmHg, right? So if that is the case, then first of all, this change in pressure from 0 to T degree centigrade, the pressure is decreased and becoming 755.4 minus 0.34 times T mmHg, right? Now, how much is the temperature change associated with this pressure change? If you have to consider from this thing, then it will be is equal to, for delta P is equal to 755.4 minus 0.34, T is equal to 0.0072 into 755.4 minus 0.34 times T divided by 760 in mmHg. Sorry, not mmHg, but this is in degree centigrade, okay? So then your actual triple point temperature is T degree centigrade, which is equal to 0 degree centigrade was the initial case, then the change in temperature for the change in pressure to triple point is this delta P. So you add that temperature change, that will give you the final triple point temperature value. So this is 0.0072 into 755.4 minus 0.34 T divided by 760. So your T is becoming 0.007156 degrees centigrade. So this is the final answer. You can check that this answer is what you are getting. Sorry. So this is your option number A, correct answer. Now question number 4 is calculate the specific heat of saturated vapor from following data. Latent heat of vaporization is given in calorie per gram units, and boiling point of water is given. DLDT is given. Then the specific heat of water at 100 degree centigrade is also given. You have to calculate the specific heat of the vapor, right? So the equation you have to use have to be identified first. Okay, so first let us write down what information we have, then solve this. So here it is given that the vaporization's latent heat is basically 539.3 calorie per gram, right? Now the boiling point temperature of water is 100 degree centigrade, which is 373 Kelvin. So the phase changes occurred between water to vapor, okay, and this dL by dt is the rate in change in the latent heat for the unit change in temperature, which is given as 0.64 calorie per gram Kelvin. Then the specific heat of water at 100 degree centigrade is equal to 1.01 calorie per gram Kelvin, right? So you have to start with the Clausius equation, obviously. First, because that involves the specific heat and the latent heat and temperature. So Clausius equation is that the change in entropy from initial to final stage is basically L by T. Right, so this is a change in entropy that you know that L is basically the amount of heat or energy, and you know that heat energy is basically T times ds, where ds is the change in entropy. So the change in entropy is, in other terms, energy by temperature, or in this case latent heat by temperature. Okay, so this is the change in entropy from initial stage to final stage per unit mass. Okay, so then ddt of L by T is equal to, taking the temperature derivative, so dsf by dt, dsi by dt. So this is 1 by T dl dt minus L by T square, which is like dsf dt minus dsi dt, right? So this is like dl dt minus L by T, so take the temperature, multiply to the right hand side, so T, now dsf by dt minus T dsi by dt. So here your dl by dt is like L by T plus Cf is minus Ci is. So this is a specific heat defined like that because you know that specific heat is the rate of change, how much heat is needed for a certain unit change in temperature. So this is dq dt in simple terms. This is the specific heat given by C. And you know that dq is simply TdS, so this becomes TdS by dt. Okay, so this is your idea of specific heat, and in this case this is the final state specific heat corresponding to this part, and this is the initial state specific heat corresponding to this part, right? So then your equation, main equation becomes the dl dt is equal to this thing. Now you have to calculate from the question that what is the vapor specific heat of the saturated vapor. So in this case the phase transition is happening from liquid to vapor phase, right? So this is your initial stage as liquid and this is your final stage as vapor. So you have to calculate what is your specific heat of the vapor stage or the F final stage. Okay, and the initial stage is the water stage specific heat, which is already given in the question at 100 degrees centigrade is 1.01 calorie per gram Kelvin. So this makes that thing easier, that your Cf is simply just then dl by dt minus L by T plus Ci, right? So your dl by dt is given in the question, that is 0.64 with the minus sign, minus L is simply 539.3 divided by T in Kelvin is 373 Kelvin, right? Then plus Ci is simply 1.01 calorie per gram Kelvin. So this whole thing gives you the answer as 1.08 with a minus sign calorie per gram Kelvin. So this is your answer. This will be option number D that you have here. So your answer is minus 1.08 calorie per gram Kelvin. Now question number 5 is, for a single component system, the specific heat at constant pressure during first order phase transition is what? So this is a question that is a conceptual question that generally it is better for you to remember that for first order phase transition you have to remember that first order means that your first order derivative of the Gibbs free energy will show a discontinuity at the what do I say, constant pressure, yeah, so at the phase transition temperature point or whatever. So basically first order phase transition is defined like when your Gibbs free energy's first order derivative becomes discontinuous at the transition point. And for second order case, second order phase transition, because it is called second order, so the idea is that the second order derivative remains discontinuous at the phase transition point or temperature, but the first order derivative remains continuous. So that is the idea behind this naming mostly. So this will be helpful for you to understand. And in that context, if the single specific heat, so basically first you have to understand what is this term, whether how it is connected to the Gibbs free energy. So if the Gibbs free energy is G, then specific heat is the second order derivative of the Gibbs free energy, right? So I will explain in more details later on. First just see that this is the second derivative of Gibbs free energy G. So if this is the second derivative, then for first order phase transition this will not be continuous, but the first order derivative is continuous. So that is the entropy. Entropy is the first order derivative, and this is discontinuous or disjoint at the phase transition point temperature Tc. So if entropy is discontinuous and C is on the other hand is, you know that this is T ds dt. So C has a dependence on S, that it is the first order derivative on S, right? So by that thing you can say that if this is your first order derivative, then if S is discontinuous at Tc, then at Tc C will be infinity, right? Because if something is, some quantity is discontinuous at some point, then if you take another derivative on that, that will give you infinity at that point. So by that your answer is infinity. So answer is infinity, that the for a single component system the specific heat at a constant pressure or Cp during first order phase transition will be infinity. Now let me explain in more details what I am trying to say is that first of all let me define the different quantities. Okay, so let's say our Gibbs free energy is capital G. Gibbs free energy is the thermodynamic potential, you must have known from the lectures. Okay, and there is a relation that dg is equal to minus s dt plus v dp. This is one of the equations in thermodynamics, very well known. So if that is the case, then you can see that s is simply minus del g del t at constant p when dp is 0, and v is del g del p at constant t when this dt is 0. So these are s and v. Okay, so if this is entropy, then what is your specific heat? Specific heat is basically Cp, if you say as per the question, it is specific heat at constant pressure. So Cp is simply T ds dt or del s del t at P constant. So this is simply T with, you replace S here, substitute S here. This is minus T del 2G del T2 at constant P. So this is the specific heat, which is the second order derivative on Gibbs free energy. So from here you know that entropy and volume are first order derivatives of the Gibbs free energy, and specific heat is second order derivative of Gibbs free energy, right? So by that definition, and the definition or the prime rule you have to remember is that first order phase transition is defined like when first order derivative of the the Gibbs free energy is showing discontinuity at phase transition point. So mostly we define the phase transition point by some temperature. Let's say this is T equal to Tc is a critical or phase transition point where the first order derivative will be discontinuous, then it is called a first order phase transition. And if the first order derivative of Gibbs free energy is discontinuous, like say S and V will be discontinuous for first order phase transition at the phase transition point Tc. And so the second derivative of Gibbs free energy, which is in this case is a specific heat. Okay, so specific heat is also first derivative on entropy S. So if your S is discontinuous, then C will be going to infinity if S is discontinuous at Tc. And the second order phase transition is when second derivative of Gibbs free energy, which is in this case is C, is discontinuous at the phase transition point Tc, but the first derivatives are all continuous, like S and V are continuous at Tc. So this you can say, like, if it is a first order phase transition, then how do you define this? So for first order phase transition, your entropy versus temperature. So if this is your entropy versus temperature, so first order means the entropy is discontinuous at Tc, right? So this will look like this thing. This is, let's say, the initial state, and this is, let's say, the final state. And this entropy is simply minus del G del T at P constant. And this is the phase transition point, which is at T equal to Tc. So here entropy is discontinuous at that transition point, because this is the first order derivative and this is a first order phase transition, in short PT. This is the first order phase transition case where the entropy is discontinuous. So the second derivative of the Gibbs free energy, which is specific heat, which is like minus del 2G by del T2 minus T times del 2G by del T2 at P constant versus T if you plot. So this is the phase transition point T equal to Tc, and here it will become like, here it will be like, I'm drawing it all wrong. Yeah, so somewhat like this, that this is the thing, this is going to infinity, and this is the initial stage, and this is the final stage. So right at the phase transition at Tc, when it is going from I to F, the specific heat is diverging, right? And so this is the idea. But for this is also for first order phase transition case. Similarly, if you plot maybe the volume, because volume is also first order derivative, so volume will also be discontinuous at the phase transition point for first order phase transition. So if this is the plot, then this will be your Tc. So this will be like this one, sorry, and this one. So this is your stage I and this is your stage F. Okay, and this is becoming disjoint at the phase transition point. So this is also first order phase transition. And finally, for first order phase transition, if you ask what is the Gibbs energy G will look like, so G versus T if you plot, that will be simply continuous at the phase transition point, right? Because the first order derivative is discontinuous, but the Gibbs energy is it's at the phase transition point is showing no discontinuity at the phase transition point. But like volume and entropy, they are showing discontinuity right at Tc, because they are the first order derivative defining the first order phase transition, and the second order derivative because this is the derivative on S, which is already discontinuous at Tc. So something where the actual quantity is discontinuous at some point, then if you take the derivative on that quantity, so that will be diverging at that point, right? Point of discontinuity. So that is why you are seeing diverging nature, diverging derivative of discontinuous function St at Tc. So this is the idea. Okay, right. Now let us move on to the next question. That which order of derivative of Gibbs energy is discontinuous for a second order phase transition. Now just now I discussed the whole thing, so this becomes now clear to you hopefully, that when they are asking second order phase transition, then obviously the first order derivative will be continuous, but the second derivative will be discontinuous. So second derivative can be specific heat, they are not mentioning it, but in general any second derivative on Gibbs energy will be discontinuous if it is a second order phase transition. So the answer will be 2, second order. So this is also the correct answer, as you can see. Now question number 7 is about Clausius-Clapeyron's equation holds for. So this is also a technical like a simple question on conceptual question. So this hopefully you have known from the lecture material itself that this only holds for first order phase transition. So that is defined for first order phase transition. So our answer will be Clausius-Clapeyron equation holds for first order phase transitions. So then question number 8 is given L equal to some function of T A plus BT plus CT squared, then find the difference of specific heats of liquid and saturated vapor. Okay. So again specific heat difference you have to calculate. So you probably remember a formula that you have used for a question just 2-3 questions before this. So there we had a formula defined for that, so you have to use exactly that formula, and here you have L in terms of T. So let us start, and the formula I am talking about is this one. You can see there is a difference in specific heat. From here you can take it out, and the rest of the part you can know from the information given to you, dl by dt and L by T. These are the parts that you can take from the question itself. So question number 8 is L is equal to A plus BT plus C T square. So then you know that dl by dt is equal to L by T plus Cv minus Cl, vapor phase minus liquid phase. There is a difference in specific heat. So Cv minus Cl will be like dl by dt minus L by T. So your L is given as A plus BT plus CT squared. So dl dt is simply B plus 2CT, and L by T will be like A by T plus B plus CT. So this is equal to B plus 2CT minus A by T minus B minus CT. So this B and this B cancels out, and this is just CT minus A by T is equal to your Cv minus Cl. So the answer is CT minus A by T. This is the difference in the specific heat, and this matches with option number A. You will see Yeah, Ct minus A by T is your correct answer, is option number A. Now question number 9. When ice melts, its volume decreases. So with increase of pressure, the melting point of ice decreases or increases, or no change or cannot be determined. Which one is correct? So again here the Clapeyron's equation will be have something that we have to guess the answer from. That the equation you have to use is the Clapeyron's equation, which tells that dp dt is equal to L by T into V2 minus V1, right? So if ice melts, then the volume increases. So here the process is ice is melting into water. So if this is the initial state, this is the final state. So ice volume is Vi and let's say water volume is Va. And you know that for this case, particular case, the thing is negative. The slope of the P versus T diagram is negative because here the volume of ice is actually greater than the volume of water. So you are decreasing volume when you are changing from ice to water. So your Vf is less than Vi. Okay. So your dV is negative when you are going from ice to water. What is the increase in pressure? So with the increase in pressure, the melting point will be what? So if dP is positive, that is the pressure is increasing. Okay. So what will be the temperature change of melting point of ice? So from here you have to use the Clapeyron's equation, that if your here Vf is basically same as V2 the final state and Vi is same as V1. So if Vf is less than Vi or if V2 is less than V1, then V2 minus V1 will be simply negative because this is volume is decreasing. Okay, so this term here is negative. Melting point temperature T cannot be negative, so this is positive because this is in Kelvin, right? So this is always positive. L is a latent heat, so this is also positive. dP in the question it is asking that for increase in pressure, that means dP the pressure change will be positive. Then what is dt? So dt is depending upon all the other terms, that this is T times V2 minus V1 into T times V2 minus V1 into dP by L, where L is positive, dP is positive, T is positive, only V2 minus V1 is negative. So if dV is negative here or V2 minus V1 is negative, then dt will also be negative. So the answer is that by this case, the melting point temperature will decrease. So temperature will by pressure increase. So the correct answer is temperature decreases, which is also the correct answer. Now question number 10 is the last one here, that in a saturated solution of table salt NaCl, which is sodium chloride, is in equilibrium with crystalline NaCl. Okay, so there is a solution of the salt NaCl and there is a crystalline solid part of NaCl, and that both of them are in equilibrium. So the number of independent intensive variables F is what? So there is a specific formula for this, very well known, that when you have to know, when you have to calculate what is the number of independent variables F, so basically it is some kind of degrees of freedom. So that is simply, there is a relation that F equal to C plus B minus 2. So let me write this down as well, that question number 10 is number of independent variables, or in other terms degree of freedom, some equilibrium mixture equal to F equal to C plus B minus 2, right? So if F is the degree of freedom, then C is the number of components present in the mixture, and P is the number of phases that is present of the element in the equilibrium mixture. Okay, so in this case the two phases are there. One is crystalline NaCl, which is a solid phase. Another is a saturated solution, which is non-solid liquid phase. Solution of NaCl, so basically it can consider as liquid, and this is solid. So this phase number is 2, and number of components is 1 only, because only NaCl, sorry, number of components is 2, because obviously to make a solution you have to take both NaCl and water. NaCl plus water is making the whole solution, so there are 2 components. So then what is your F? F is basically C, that is 2, P value is 2, C plus P minus 2. So this 2 and 2 cancelling out, F is 2. So the degree of freedom is 2, that means the number of independent intensive variables in this case is 2. So the correct answer will be 2, which is this. So option number C is correct. So with this we finish the week's assignments practice problems. Okay, and with this I would also like to discuss some extra problems which I think will be relevant and will be of use and related to this topic only. So let me discuss that part as well. Okay. Just 1 second. Okay, so this is an interesting question. Maybe 2-3 questions we'll discuss, then we'll finish this one. So extra question 1. So this question is that the vapor exit tube of a pressure cooker has a radius of 2 mm. So you have a pressure cooker, vapor exit tube. You have all seen pressure cookers, I hope. So vapor exit tube of pressure cooker, you have seen that it is a sort of circular thing, so it has a radius. So not circular, but this is that is a cylindrical part, but it has a radius obviously. So exit tube has radius of 2 millimeter, and it is closed by a mass of 140 gram fitted at its mouth. So this tube is closed by mass of 140 gram, which is the mass in this case, fitted at its mouth. So what is the boiling point of water inside that cooker? What's the boiling point of water which is inside the pressure cooker? And the additional information they have given is the latent heat of vaporization of water is 540 calorie, and the specific heat, or sorry, the specific volume of water vapor, is 1674 cubic centimeter of cc. Right, so by this you can see that you have to calculate what is the boiling point of temperature. So uh, first of all, what comes to your mind is that uh, you have to understand that what is the uh, like how the pressure cooker is actually working in this case, that the vapor is forming inside the pressure cooker when the water is transformed into vapor by when it is heated up, and that vapor will try to force out from the exit tube of the pressure cooker, and it will only force out from that tube when the vapor pressure exceeds the pressure due to the imposed mass. That means that there is a certain mass that is actually tightly fitted to the exit tube, right? So that is holding it from opening up, but it can hold as long as the vapor pressure inside is not too much to exceed the pressure created by the mass fitted to its mouth. So once that pressure is exceeded, the vapor pressure is too large that it is exceeding the mass fitted to the exit tube, and that mass is pressure due to that mass. So then it comes out from the exit tube, right? That is the idea of pressure cooker. So in this case, it is mentioned that, so if there is a 140 gram of mass fitted to its mouth, then how much pressure does that create on the mouth of the exit tube? So the answer is caused on mouth of the exit tube by the 140 gram mass fitted to it is equal to, let's say this is delta P. So this is the pressure amount that is needed for the vapor of water inside to exceed if it wants to come out, if it has to exit from the exit tube. So then this much pressure it has to attend at least. So that is delta P I am defining here. So delta P is basically 140 gram, how much pressure that will give. So the mass 140 will give a force of m times g, right? So this is, the idea is that pressure is equal to force by area. So force is here m times the mass into the gravitational acceleration divided by the area is simply pi r square for a circular radius of r. So here mass is 140 gram into g is 980. Both are in CGS units, and pi into r squared. So r is here 2 millimeter. So 2 millimeter is 0.2 centimeter. So 0.2 whole squared. Okay, so this is actually, if you calculate, this will be 1.092 into 10 to the power of 6 dyne in CGS unit, dyne per centimeter square. This is the pressure that is caused by the exit tube cap that is put by in terms of a 140 gram mass. Now from the Clapeyron's equation you have to again use, because that involves all the needed quantities. So Clapeyron's equation tells you that dP dt is equal to L by T Pf minus Pi. Okay. So delta P is nothing but the change in pressure from the initial stage to final stage. So 1 to 2. So let's say P1 is the initial one and P2 is the final one. So this is the thing. So this is P2 minus P1 is the change in pressure. And this is basically L by T Vf minus Vi times dt. T is going from T1 to T2. So this is L by Vf minus Vi, and ln of dt by t integral will give you a ln t, and this is moving from T1 to T2. So this is simply L by Vf minus Vi ln of T2 by T1. Okay, so then ln of T2 by T1 is simply P2 minus P1 into Vf minus Vi by L, right? So P2 by minus P1 we just calculated from the pressure caused by the 140 ton mass, which is 1.092 into 10 to the power 16 dyne per centimeter square into V2 minus V1 is simply 1674 minus 1. Why? Because 1674 is the specific volume caused by the water vapor. Okay, and so vapor phase, this is 1674, and for the initial stage water we take it as 1 cc. Okay, so for that case, if you have that information, then you have to also substitute L, which is like 540, because you have to convert everything into CGS. So just convert into arg units, which is calorie per to arg is 4.2 into 10 to the power 7 factor multiplied. Okay, so this is the whole thing is becoming, if you calculate, it will be 0.08. So this is ln of T2 by T1 is equal to 0.08. In that case, if you convert T2 by T1 is equal to then e to the power of 0.08, which is like 1.084. So then T2 is equal to T1 into 1.084, and T1 is simply T373 into 1.084, which is like 404 Kelvin. T2 is that, which you can convert into degree centigrade as well by minus 273, which is like 131 degree centigrade. So this is the boiling point of water inside the cooker, obviously, because this is the T2 value. So your temperature when it is boiled or water is boiled, so its temperature is always already increasing by that. So the final temperature is your boiling point temperature. So because you know that as long as the temperature is changing, the phase is not changing. So when the water's temperature is rising and rising, so increasing, so finally when it reaches T2, which is 131 degree centigrade in this case, so then it already reaches the temperature when it will get converted into vapor, or it will get vaporized. So then the temperature during vaporization remains constant. Then only the phase changes. The temperature remains constant. Phase changes by the latent heat L, and the temperature remains at 131 degree centigrade. So this, you can see that this is greater than 100 degree centigrade, which is the usual conditions boiling point of water. But you know that inside pressure cooker, that thing is, the water is vaporized at higher temperature than usual. So this is why this is at 131 degree centigrade, and this is the mechanism of pressure cooker, basically, that you have caused, you have enclosed something in a pressure, and by a result of that you increase the boiling point of water inside, so that it is easier to cook. It is easier to cook things inside that pressure cooker than it will be in normal conditions. So that is a very interesting question regarding how the pressure cooker mechanism works, involving the thermodynamic relations related to that. Okay, so this is one good question. Then there are mostly questions based on these, either the Clapeyron's equation you have to use, or the other one involving the dl by dt specific heat, sorry, the latent heat change rate equation. So these are the main two things that will become most often in such questions. Okay, and what else we can discuss is, let me see. Yeah, another question, maybe it will be conceptual and helpful. That extra question number 2, that for a thermodynamic system, the question is that for a thermodynamic system, your U is 3 by 2 PV. So U, you know that is the general notation for the internal energy. P and V are the pressure and volume, and the pressure is AV T to the power of 4. Okay, and find the Gibbs potential and the Helmholtz potential. So what is the Gibbs potential G, and what is the Helmholtz potential, which is F? These are the two questions asked, and U is given, P is given. So you know that generally the thermodynamic relations that are well known is TdS equal to du plus PdV, right? So and in such case, you know that F is equal to U minus Ts. That is how the Helmholtz potential is defined, that it is U minus Ts, and G equal to U plus PV minus TS, or this is also called enthalpy. Enthalpy minus TS is your G. So if you have to get what is F and what is G, then you have to know all the terms involved in here. Like T will remain as it is. U is already given in the question. In this case, PV is remaining as it is, like T. U is given in the question. But the one thing that we'll need for both of them is entropy. So entropy is something you have to calculate given the option you have about the information about U. So if you want to know S, then you can substitute and get the expressions for F and G. So this is one expression that standardly includes ds, du, and all other temperature and pressure variables. So from here you can get S. How? It is that du is then d of 3 by 2 PV plus PV is simply P is given as AV to the power of 4 dV. So this is 3 by 2. Then V is, let's say it is, we are only taking the constant part outside. The rest of the part is P times V, where P remains, substitute P as AV to the power 4, and when it is multiplied by V, so this is AV square to the power of 4 plus AV to the power of 4 dV. Okay. So this is 3 by 2 into A 2V to the power of 4 dV plus AV squared 4 t cube dt plus AV to the power 4 dV. So this 2 and 2 cancelling out. So this is 3AV to the power of 4 dV plus this 2 and this 4 makes it only 2. So this is 3 times 2 is 6. 6AV squared t cube dt plus the last one is AV t to the power of 4 dV. Okay. So sorry. Again, this is your TDS. So from here, if you just take the temperature common, so then TDS equal to simply 3, sorry, this thing and this thing gets added, so this is 4 A V to the power 4. Now if you multiply 1, so if you take common 1t, so this is simply t cube dV plus 6A V squared, this becomes t squared by taking 1t as common, so this cancelling out. So ds is becoming, now we have to take a close compact form within the derivative so that you can take out what is entropy. So this is simply ds equal to, if you take common 2a, so this remaining term is 2v t cube dv plus 3v squared t squared dt. So this is 2a, then derivative on v squared t cube. Why? Because if you take a derivative on v squared t cube, it becomes 2v t cube dv plus on the second term, if you take the derivative, it becomes 3v squared t squared dt. So this is your derivative term, and so if you take out the derivative separately, so s becomes remaining term, that is 2a v squared t cube. So this is your entropy expression. So once you have got that, the rest of the terms are already known, that F is equal to simply U minus TS. So this is just a simple sum we have done just to make the connections between the thermodynamic relations and potential even clearer. So U is basically 3 by 2 PV minus T is 3A V squared T to the power 4. Okay, and P you can substitute. P is some A V t to the power 4. So this is, the whole thing will become minus half A V squared to the power 4. Simply for G, you can take, this is U plus PV minus TS. Now you put the value of S, you put the value of U and value of P. Then by that you will get, this is half A V squared to the power 4. So with this we are done with this week's tutorials, and we'll meet in the next week.